Okay, for this example, we're trying to figure out how many relative maximum and how many relative minimum values we have. They give us the graph of f prime. And so we first want to figure out where f prime is either positive or negative. So f prime is going to be positive where the graph is above the x-axis. And f prime is going to be negative when the graph is below the x-axis. Now let's fill out our chart. Okay, I think you can see that something special is happening at point E, and something special is happening at point H. And so our original function actually decreases all the way until you get to E, and then from E to H, our original function is increasing, and then after H, our original function is going to be decreasing. The question is, how many relative minimum and how many relative maximum values do we have? In this case, we have one of each. We're going to have a relative minimum at x equals E, and we're going to have a relative maximum at x equals H. Okay, now we're looking at the exact same graph, and it's still f prime. We haven't changed anything. But now we want to find inflection points. So we need to look at concave up and concave down to figure that out. So we need to figure out f double prime, but all we have is f prime. So the way to find f double prime is to do the derivative. The derivative of f prime is going to be f double prime. And remember, the derivative is the same thing as the slope. So we need the slope of f prime. So we need to figure out what the slope of this graph is. And that'll be the second derivative. The slope of this graph is going to be positive here and positive here. Then the slope of this graph is going to be negative here and also negative over here. And those pluses and minuses are the polarity of the second derivative. So now we can fill out our chart. Our second derivative is going to be positive before you get to A, and then negative until you get to C. Then positive until you get to G, and negative afterwards. Okay, if we just pay attention to the concave up and concave down part, our original function will be concave up, and then concave down, and concave up, and then concave down. So our inflection points are going to occur at x equals A, C, and G. And again, the question just asks, where does f have its inflection points? So they just want the x values. So our final answers are going to be x equals A, C, and G. Okay, now we have to graph f given f prime. So they give us the graph of f prime. We have to figure out what f is going to look like. So what I like to do is start with the increasing and decreasing. So our original function f is going to be decreasing when f prime is negative. So this is where f prime is negative. Obviously, that's when the graph is below the x-axis. And then f prime is going to be positive here because that's where f prime is above the x-axis. So that means our original function is going to be decreasing until you get to E, and then increasing until H, and then decreasing afterwards. The next thing we're going to do is we're going to add the concave up and concave down part. So to do concave up and concave down, you need f double prime. We don't have f double prime, but we do have f prime. So if we just do the derivative of f prime, that will equal f double prime. So the derivative of f prime is the same thing as the slope of f prime. So let's look at the slope of f prime. We have positive and we have negative. And that's because the slope is positive here and the slope is positive here. And the slope is negative here and the slope is negative here. So those pluses and minuses are the values of the second derivative. So we know that we are concave up until we get to A. Now we're still going to be decreasing, but we need to be decreasing and concave up. So it's going to look something like this. I also want to point out that the derivative is going to equal 0 at x equals A. So we need a horizontal tangent line there. Then we're going to be concave down all the way to C. So concave down, but we still need to be decreasing. Then from C all the way to G, we should be concave up. I want to point out that at x equals E, the slope should be 0, so we should expect a horizontal tangent line at x equals E. Then we're going to be concave down after x equals G. We also need a slope of 0 at x equals H. So we want a horizontal tangent line at x equals H, but also concave down. Okay, I need a horizontal tangent line here at A. I want to fix that just a little bit. There we go, that looks better, and now we can erase all those straight lines. Again, I want to point out that we should have a slope of 0 when x is equal to a, e, and h. Let's take a look at that. You can see that it does look like we have a horizontal tangent line at a, e, and also h. And again, our function should be decreasing all the way to e. So notice we are decreasing all the way to e, then our function increases until h, and then decreases again after h. So this is a pretty good sketch. Now I also want to point out that the height does not really matter. So you can actually move any of these points up or down and it would still be correct. Okay, sometimes the AP test will try to give you two different functions like they do here. They say that g is a function whose derivative is f. So that means f is the derivative of g. And what I would recommend doing is just relabel the graph so it's not confusing. So we're going to cover up this f with a g prime. Now it's going to be really easy to figure out g prime and g double prime. Since this is the graph of g prime, if we're looking for g prime of 7, then you just go to x equals 7, and you can see that g prime of 7 is just going to equal 2. Same thing with g prime of negative 6. If you just go to negative 6, you can see that you get negative 1. Now the second derivative is going to be a little bit harder. Remember, the second derivative is the slope of the first derivative. So that would be the slope of this graph. Now when you have lines, the slope is the same everywhere on that line. So for this line, you can see that we go up 1 and right 2, up 1 and right 2, up 1 and right 2. So that means 1/2 is going to be the slope of that line. For the line in the middle, you can see that we go down 1 and right 1, down 1 and right 1, down 1 and right 1. So the slope of that is going to be negative 1. And the last line segment, you can see that we're going up 1 and right 1, up 1 and right 1, all the way to the end. So the slope there is just going to be positive 1. So now if we're looking for the second derivative when x is 7, that's this point right here. We know the slope everywhere on that line is going to equal 1. So then the second derivative when x is 7 is going to equal positive 1. The last one? Okay, the last one is asking what is the second derivative when x is equal to negative 6. You can see that's going to land on this line over here. And the slope everywhere on that line is 1/2. So the second derivative at x equals negative 6 is going to equal 1/2. And that's it. Okay, this is the exact same problem. It looks like maybe part B or something like that. Remember, we renamed it from f to g prime. And now they want us to find the equation of the tangent line to the graph of g at x equals 1. They do give us a point. It says g of 1 is equal to 5. So that's our point. And then we're going to use this graph to figure out the slope. When x is 1, g prime is negative 2. So that means the slope is going to be negative 2. Once you have a point and a slope, you're pretty much done. You can write your equation of your line. Equation of the line is going to be y minus 5 equals the slope and then x minus 1. You could stop there or you could solve for y. If you solve for y, you're going to get y equals negative 2x plus 7. Put a box around it. There we go. That is the equation of the tangent line to the graph of g at x equals 1. Okay, again, this is the exact same example. This is probably part C. They want us to describe the second derivative as a piecewise function. Now, we already calculated the slope of each of these three line segments. The first one was 1/2. Remember, the slope is going to be the same everywhere on that line. The second one was negative 1. So everywhere on this line segment, the slope is going to be negative 1. And the last line segment, the slope was positive 1. So everywhere on that line segment, it's going to be positive 1. And remember, that's the slope of g prime, so that's g double prime. So when x is between negative 8 and negative 2, the second derivative is going to be 1/2. From negative 2 to 2, the second derivative is going to be negative 1. And from 2 to 8, the second derivative is going to be positive 1. And that's it. That is the second derivative described as a piecewise function. Okay, for this example, they're asking us to describe the shape of g near x equals 5. I want to point out that g prime of 5 is 0. And remember, the slope here was 1. So everywhere on this line, the slope was 1. So that means the second derivative at 5 is going to be a positive number. So when your first derivative is 0 and your second derivative is positive, according to the second derivative test, you're going to have a minimum value at that spot. Again, the second derivative being positive means you're concave up, and the first derivative equals 0 means you have a horizontal tangent line there. And so that's the reason why you would have a relative minimum at that spot, according to the second derivative test. Okay, another acceptable answer would be to say that you have a horizontal tangent line and that you're concave up. But the best answer is to say that you have a relative minimum according to the second derivative test, because your first derivative is 0 and your second derivative is positive.